Hi there, I'm Seth, and in this video I'm going to explain the Spearman-Brown prophecy formula. Not only what it does and how to use it, but why the formula works. My goal is to build your intuition through visual representations. Too often we accept the legitimacy of the formulas we're given in stats class or psychometrics class without really understanding how they work at a fundamental level. I think this is a serious mistake. I personally don't trust any mathematical formula unless I understand it in my bones, because otherwise I don't really know if it does what others claim it does, and I don't really know if I'm using it correctly or not, or if my conclusions are accurate. Unfortunately, despite searching, I've never found an intuitive explanation for this formula. I've never even seen someone attempt to explain how this formula works in an intuitive way. And that's after looking through psychometrics books, videos, blog posts. Even Brown and Spearman, the dudes who independently developed this formula, they didn't actually explain it. They just mathematically proved that it worked, and then they moved on. But if there is a mathematical proof, that means there is also an intuitive explanation if you're willing to search for it. So I decided to tear the formula apart and figure out what's going on, and that's what I'm going to show you in this video. In the next video, I'll also show you how to set up the formula in Excel and R, and I'll work through some practice problems. Fortunately, the formula is not as complicated as it might look at first glance. And here's a bonus. Truly understanding how the formula works will unlock your understanding of other related formulas. Like, for example, compare it to this formula for correcting range restriction. If you don't know what that means, don't worry about it right now. The point is, I think you can see some pretty clear similarities between these two formulas. Granted, for the range restriction formula, I've changed some of the traditional notation, and I've also rearranged the formula so the parallels would be more obvious. But when you look at these two, even if you don't really understand what they're doing, I think you can see that they're both using the same fundamental trick. In this case, they're both using the same trick to estimate what a particular correlation would be if the situation were different. Specifically, as we'll see, for the left formula, that's telling us about how a correlation would be expected to change if the test length were changed. On the right, it's about how a correlation might change if there were a different amount of variability in the data. And this is actually one of the keys to understanding psychometrics. When you really deeply understand one formula, that's going to unlock your understanding of so many other formulas, because a lot of the stuff we do in psychometrics, it looks different, but it's really using the same handful of basic tricks. But enough foreshadowing, let's get into it. The Spearman-Brown prophecy formula, also called the Spearman-Brown prediction formula or just the Spearman-Brown formula, allows us to estimate what the reliability of a scale would be if we changed the number of items, or the number of raters if you're thinking about inter-rater reliability. So more generally, it tells us about how the reliability would change if we changed the number of measurements. Now, I know some of you already understand reliability and already know what the notation means. You're just here for a quick and dirty explanation. So I'll get that out of the way in a second, and then I'll spend the rest of this video going through everything step by step for those who are less familiar. If you don't know what any of these symbols mean, or you don't understand the jargon I'm about to use, you can skip this part because I'll come back and explain it more thoroughly later. In brief, the numerator scales your original reliability estimate based on the test length, and then the denominator yanks that result back onto a 0 to 1 scale because reliability is supposed to range from 0 to 1. Quick example. Suppose our reliability estimate is 0.7 and we double the test length, meaning n equals 2. When we double the test length, we double the relative amount of true score variance, which knocks us off our 0 to 1 scale. It's obvious in this case because our reliability estimate would become 1.4, even though it should not be higher than 1. So the denominator takes that 1.4 value and yanks it back onto a 0 to 1 scale. You can see here how it drags it down from 1.4 to 0.82, which is within the bounds we were expecting. Exactly how it does that will be revisited later in the video after I've laid the groundwork for those who are newer to reliability and the Spearman-Brown formula. Now, if that's all you needed, then you're good to go. Get out of here, have fun, make good choices. But if you want a more in-depth explanation, including intuitive visualizations, demonstrations in Excel and R, etc., then stick around. The rest of this video will focus on the fundamental process of how reliability changes as a function of test length. Because when you understand that, how and why the Spearman-Brown formula works will become obvious. Fair warning, I'm going to go pretty deep into this topic. The rest of the video is really only for someone who wants to understand this formula inside and out, but I promise to explain each step in the simplest, most comprehensible way I can think of. Toward that end, to understand how the formula works in full detail, you're going to need to understand two fundamental psychometrics concepts: reliability and the principle of aggregation. If these terms are not familiar to you, I strongly recommend checking out my introductory video on reliability and the principle of aggregation, which I created specifically to provide foundational knowledge for this video. If you don't have a fairly intuitive understanding of these concepts, the Spearman-Brown formula is probably going to remain gibberish to you. Here is a very brief refresher. Classical test theory says that an observed score reflects the individual's true score on that test or scale, but there's some amount of random error as well because a billion random variables jostle around that person's response to each item. The random errors are assumed to be normally distributed around whatever the true score is. This means errors are as likely to be overestimates as underestimates, which also means that the errors should cancel out on average. We can extend this concept to see that some of the variability in a distribution of scores is due to genuine, true differences between individuals completing the test, and some of the variability is just due to randomness. Here's a visual representation of this idea, where there are 4 true scores represented by blue bars, and you can see that the observed scores, represented by black bars, missed the mark by some amount of random error. Some of the variability in the distribution is due to genuine differences among people on whatever characteristic you're measuring, and some of the variability in the distribution is just due to randomness. Reliability is the proportion of the observed variance that is attributable to true score rather than randomness. Here's a formula that represents this idea, where reliability is denoted by RxX. Reliability asks, how much of the variance is true score variance? The principle of aggregation essentially states that because random errors are as likely to be overestimates of the true score as they are to be underestimates, they'll tend to cancel out when you add them together. And this is increasingly true as we increase the number of observations. So, taking all of this together, we can conclude that increasing the test length should increase the reliability, at least assuming the new items are comparable to the original items. This is because the more good items we've got, the more that individuals' observed scores will tend to converge on their true scores. As a result, there's less random error, and the proportion of variance in the data set that is true score variance will be higher. And that's what reliability is. It's the proportion of variance that's attributable to true score. Now again, if you need a more detailed explanation of anything I just said, or all of it, check the video on the right. But if you already understand these concepts, then you have everything you need to be able to understand the Spearman-Brown prophecy formula. Okay, now we're at the really fun part. The Spearman-Brown prophecy formula estimates how much reliability will increase or decrease based on how many measurements are added or removed. Brief explanation of the notation. RxX star is what I use to represent the estimated new reliability. So what the reliability is going to be after the test length is changed. RxX without the star is the current reliability, which is based on the current test length. And then lastly, we call the factor by which you adjust the test length n. So it's a scaling factor. For example, if we double the test length, that means n equals 2, because the new length will be 2 times the current length. Or if we quadruple the test length, then n equals 4. Or what if we cut the test in half? That means n equals 1/2. N is the factor by which you multiply the current test length to get the new test length. First, I'm going to provide a visual explanation of the relationship between reliability and test length because that's going to be more intuitive. And then I'll show you how the formula is capturing that same idea. Let's start with a scenario where half the variance is attributable to true score and half is due to random error. What is the reliability here? Think about it. Reliability is the proportion of variance that's attributable to true score, and here that's half of the variance, so reliability is 0.5. We're dealing with a 1-to-1 ratio where we have equal parts randomness and true score. Now, suppose we doubled the test length. In other words, our scaling factor is 2. We've got twice as many items or observations. What would happen to the reliability when we doubled the test length? Well, first of all, notice that the true score isn't really changing as we add more items. I'm cycling back and forth between fewer items and more items. You can see the observed scores are getting closer to the true score when we have more items, but the true score is not changing. It just is what it is. That's a constant for each person. So when we view it in this way, the amount of true score variance is not going to change. But notice that the amount of variance attributed to randomness is going down as we add more items. Here, there are fewer items. Then when we add more items, the error part is going down. Specifically, when we double the number of items, the amount of variability attributable to random error is cut in half on average. Think that through, because this is the core logic and not many people realize that this is how it works. If we double the number of items, the random variance is cut in half. Meanwhile, the amount of variance attributable to true score is unchanged. The only exception would be if we started with a reliability of 0 or 1, because then adding or removing equivalent items wouldn't change anything. So why would doubling the number of items cut the error variance in half? Let's build some intuition for this. Imagine we only had one score per person. Recall that we expect the errors to be normally distributed around the true score. So when there's only one observed score, it can bounce around all over this distribution. It's more likely to be nearer to the true score, which is the mean of this distribution, and it's less likely to be far out in the tails. But how much it bounces around can be described by the variance of this distribution. But what happens whenever we have two scores? Now we're averaging them to get an observed score, and the average of two numbers is the midpoint between them. So I'm going to show you some examples where we have pairs of responses and we're looking at the midpoint between them. Do you see what's happening? Each individual score is as spread out as it might normally be, but the averages between these pairs, which is what ends up being our observed score, those are less spread out. They would have to be because they're halfway between the pair of scores. In other words, the averages of two items are going to be closer to the true score than single scores alone are on average. Now think it through. When you average two numbers, you start with 2 and end up with 1, which is the mean. So you're collapsing two values into one value. In this way, you are cutting the spread exactly in half on average. And remember, this distribution represents the error around the true score, and this is happening for every individual in the data set. So if we double the number of items in our test, the error variance in our entire distribution should be cut in half. And that's what's illustrated here. Now, after the random variance is cut in half, we're left with a 2-to-1 ratio. Out of what is here, 2 parts are attributable to true score and 1 part is attributable to random error. There's twice as much true score as random error. That means our new reliability will be what? Think it through. Reliability is the proportion of variance attributable to true score, which is this part, this dark blue part. So after we double the test length, which cuts the error variance in half, the new reliability will be what? A 2-to-1 ratio means 2/3 of the existing variance is now true score variance, which means our new reliability will be 2/3, or approximately 0.67. So we increase from 0.5 to 0.67 whenever we doubled the test length. This is exactly how the Spearman-Brown prophecy formula works. If that process makes sense to you, then you already intuitively understand how reliability changes based on test length. The formula is just a way of capturing that exact process I just walked you through. And in this straightforward case, you wouldn't even need the formula. You can probably just look at this and visualize that the new proportion of true score variance is going to be 2/3. So the reliability is 2/3 or 0.67. Real quick, why don't we check and make sure that I'm right? I'm going to check my work using a Spearman-Brown calculator that I made in R. I'll show you how to do this later in Excel and R, but for right now, just trust me that it works. Okay, so let's see. We started with what? 0.5, and then our scaling factor was 2. So let's run that and see. The new reliability will be 0.67. So we did that correctly. In other words, the formula came to the exact same conclusion we did through this visual demonstration. So hopefully this straightforward example is making sense to you, but we can generalize this a bit. Doubling the number of items cut the error variance in half. So what do you think would happen if we tripled the number of items? It would cut the error variance down to 1/3 of whatever its original size was. It's the same logic, except we're tripling rather than doubling. Now we're looking at a 3-to-1 ratio of true score to error score. That means our reliability would change from 0.5 to what? Take a moment, think it through. Reliability is the proportion of true score variance out of the total variance. So out of the variance you see here, what proportion is true score variance? Remember, originally this error part was half. It was the same size as this true score part. Now it's been cut down to 1/3 of that. That means we have a 3-to-1 ratio of true score variance to error variance, meaning 3 out of 4 parts, or 3/4 of the total variance is attributable to true score. 3/4 is 0.75. So when we triple the test length, we increase reliability from 0.5 to 0.75 on average. Let's check this in R to make sure I'm not just making up random things and posting it on YouTube. Let's see, our scaling factor is now 3, so the new reliability becomes 0.75, which is what we knew it would be based on this visual representation. Cool. Now, here's a fun idea. What if instead of increasing the test length, we decreased the test length? What would happen? Doubling the test length cut the error variance in half. So cutting the test length down to 1/4 of its original length would do what to the error variance? It would quadruple it. We have 1/4 as many items, so we know we can expect to have 4 times as much error variance. Not great for reliability. So now we have a 4-to-1 ratio in favor of the error variance. Uh-oh. The reliability was 0.5. Now what's it going to be? Only 1 out of 5 total parts is true score variance, so the reliability has decreased to 1/5, or 0.2. Not great. Let's just double check that in R real quick. So now we're saying, what did we say? We cut it down to 1/4. So we can say 1/4, or we could say 0.25. Doesn't really matter, same thing. Yep, reliability decreases to 0.2, as we knew it would from this visual demonstration. Now, I've used a convenient scenario where the starting proportions were 0.5 and 0.5, but it works the same way regardless of what your initial reliability is. For example, suppose we start with a different reliability like 0.7, meaning initially 70% of the variance is attributable to true score and 30% is attributable to random noise. If we double the test length, meaning n equals 2, then the error variance gets cut in half again. Now this is more difficult to see, but what we're looking at is a, that becomes 0.15. This is a 14:3 ratio. So that's 14 parts due to true score and 3 parts due to random error. So the new reliability is 14 out of 17, which is, I can't do that in my head. 14 out of 17 is 0.8235. All right, let's just check that in R real quick. We started with 0.7 as our reliability, then we doubled the number of items. Is that what we got? I've already forgotten what it is. Yeah, 0.82. So it gives the exact same result. I love that. Okay, and if you don't see how this is a 14:3 ratio, don't worry about that. That doesn't really matter. After all, we can just use the formula. You don't have to do it visually. I just wanted to demonstrate that this works regardless of what your starting reliability is and regardless of what scaling factor you use. Now, one thing I hope you realize as you're watching this is that we don't even technically need the Spearman-Brown formula. You could work out what the new reliability would be using a visual representation like this. But it starts to become a huge pain when you have less contrived examples. Like what if your starting reliability was 0.77 and your scaling factor is 4.2? It's going to be way easier to just use a formula at that point. So that is what the formula does. But before we walk through the formula step by step, I want to try something daring. Let's see if we can build our own formula to represent the process that we've been using in these visual examples. First, let's make sure we're clear on the key terms before we start using them to build an equation. Okay, so you already know Rxx is the original reliability estimate and N is the scaling factor. But let's add another term, 1 minus Rxx, which is the opposite of reliability. Reliability is the proportion of variance attributable to true score, so it's out of a maximum of 1. Therefore, 1 minus the reliability must be the proportion of variance that's attributable to error. It's all error or true scores, so they add up to 1 together. Like in our easiest example where the starting reliability was 0.5, that was 0.5 error and 0.5 true score. So what happened in that visualization? When we doubled the test length, we divided the error variance by 2, which you can see represented there on the screen. So clearly, the first part of our formula should be 1 minus Rxx divided by N. We took that error part and we divided it by the scaling factor. It went from 0.5 and it was divided by 2. Next we asked, well, what proportion is this true score amount when it's divided by all of what remains? In other words, Rxx divided by itself plus whatever remains of the error variance. So we could represent that concept here. We have the amount of true score error that we started with, and then we say how much is that out of all that's left. So true score plus the error part. This formula is literally saying how much is this section out of both of these combined. That's literally what it says. Let's just plug in some numbers real quick and see if this formula works. I'm going to use MathPapa because I like the way that it expresses fractions. So our formula says our starting reliability divided by the starting reliability plus 1 minus that starting reliability divided by 2. And whenever we plug it in, we get 0.66667, which is 2/3. So what do you know? The formula we just created gives us the exact same adjusted reliability estimate. We just created our own Spearman-Brown formula. We just created the Osborn-Brown-Spearman formula. But in actuality, no, my name doesn't go anywhere in the title because this formula that we just created is algebraically equivalent to the formula that Brown and Spearman already developed over 100 years ago. To show that, let's rearrange this formula a bit. It's kind of weird and annoying to have this fraction inside a fraction, so we can get the n out of this denominator by multiplying this times n over n. Doing that gives us this right here, and I'm going to rearrange the denominator a little bit so that it starts to look familiar. This makes the next step easier. Now I'm going to factor out this RXX from both of these terms, and we are left with this formula, which is the Spearman-Brown prophecy formula. So their formula is algebraically equivalent to what I would argue is this more intuitive, albeit clunkier, version. So this is one way to understand the Spearman-Brown formula. It's tracking how much the error part is increased or decreased, and that changes reliability because reliability is defined as the proportion of true score variance out of the total. It's less obvious to see when we've arranged it this way, but we know that it's the same as the more intuitive version, and we can confirm that it works the same way regardless of how the formula is arranged. If we plug in 0.5 for RXX and 2 for N, it spits out 0.67, the adjusted reliability estimate that we knew we were going to get at this point. But wait, maybe you're not happy with this explanation. Maybe it annoys you that the mainstream version of the formula that you see on the screen is not as intuitive as the formula we created a minute ago. Or maybe you just remember that I've already promised to give a more in-depth explanation that aligns with this version of the formula. Okay then, let's work through that as well. I gave you the quick and dirty version of this explanation at the beginning, and now that you understand the core intuition behind how reliability changes as a function of test length, I should be able to break this down pretty quickly. So we saw before that doubling the test length cuts the error variance in half. Well, this would be equivalent to leaving the error variance alone and doubling the true score variance instead. It's the same thing in relative terms. Either way, you're ending up with a 2-to-1 ratio, meaning 2/3 of the variance is true score variance. So one way to think about this is that when you double the test length, you double the relative amount of true score variance, regardless of which of these two ways you're thinking about it. And like before, a 2-to-1 ratio means 2 out of 3 parts are true score variance, so our reliability estimate adjusts up from 0.5 to 0.6. That's one way to think about what's happening in the numerator. It's doubling our original reliability estimate. But also remember that doing this knocks our estimate off of its typical 0-to-1 range. Reliability is a proportion, so it doesn't make sense to have values that are lower than 0 or higher than 1. A value of 1.4 doesn't make sense as a reliability estimate. It's like saying you had 10 slices of pizza and you ate 14 of them. You can't eat more than the total amount of pizza. Consequently, we need the denominator to yank that result back onto a 0-to-1 scale. To explain how it does that, let's rearrange the formula a little. Multiplication is just repeated addition, so 2 times the reliability is the same thing as the reliability plus itself, right? Also notice what happens whenever we simplify this denominator. It comes out to 1 plus the reliability. Do you see what is happening here? Before we made any adjustment, our reliability estimate was just RXX. It was itself, which is the same thing as itself over 1. It was whatever proportion, like 0.7, out of a maximum of 1. Then, when we doubled the test length, we doubled the relative amount of true score variance, which is the same thing as adding that value to itself in the numerator. So the denominator says, oh, you added that value up top, then we're going to add the exact same thing down low in order to accommodate that increase. Remember how I said you can't eat more than the total amount of pizza that you have? Imagine you have 10 slices of pizza. You're really hungry, so you eat 7 slices, and your friend eats 3 slices. You're still hungry, so you order 7 more slices. That's 14 for you and 3 for your friend. In this scenario, you obviously wouldn't say, I ate 14 out of the 10 slices, because when you added 7 more slices, the total amount increased to 17. Instead, you would say, I ate 14 out of the 17 slices of pizza, or about 82%. Anytime you have a proportion, the whole is made up of the parts. So if you increase or decrease one of the parts by some amount, you simultaneously increase or decrease the entire whole by that same amount. I hope this seems really obvious when broken down like this. And that's exactly what the formula is doing. If doubling the test length means twice as much true score variance in the numerator, then we're going to have to increase the denominator, the total amount of variance, by that same amount to accommodate the growth. Here's what that looks like when n equals 2 and the reliability estimate is 0.7. We added 0.7 up top, so we also add 0.7 down low to accommodate the increase. And that's what ensures that our resulting reliability estimate falls between 0 and 1, as we'd hoped it would. Now, if you were paying close attention, you might have noticed that that exactly parallels our visual solutions. Our original reliability was 0.5 out of 1, but then when the amount of true score variance is doubled, we've got two of those 0.5s. We don't say 0.5 plus 0.5 is 1, so the reliability is 1. No, we had to expand our denominator just like the Spearman-Brown formula did. So we take that change into account and we say we've now got 2 parts true score out of 3 parts total. Our denominator has changed because we added a new part to the numerator. So once again, this visualization is doing the exact same thing as the formula. It is the same procedure viewed in 2 different ways. And no matter what scaling factor we use, that is, no matter what value of n we use, there's an equivalent way of representing the formula like this, where we're either adding the same amount to the top and bottom, or we're subtracting the same amount from the top and bottom. Let's look at a couple of examples. What if we triple the test length? That means n equals 3. And you can see once again, it's possible to rearrange this formula so that we start to see we started with a reliability estimate expressed out of 1, and then we added 2 values of RxX up top, so we also added those 2 values down low. This is a rearrangement of the familiar formula. I think when you start to see it this way, the denominator of the formula starts to become less mysterious. We start at 1, which was the maximum possible reliability estimate, and then we say, whatever n is, we're going to subtract 1 from that number, and that tells us how many extra values of RxX we need to add in the denominator to counterbalance what's happening in the numerator. For example, multiplying the reliability times 3 is the same thing as adding 3 minus 1, aka 2 more values of the reliability. So we need to add 3 minus 1 equals 2 values of the reliability to the denominator as well, because that's part of the total now. The entire formula actually makes perfect sense when you break it down like this. But what if we reduce the test length rather than increase it? What if we cut the test length down to 1/3 of its original length? Rather than tripling it, we divide it by 3. Well, this is a bit less pretty to look at, but it's the exact same process, only we're subtracting now rather than adding. Just like multiplication is repeated addition, division can be thought of as repeated subtraction. I promise this is not as scary as it looks. Recall that dividing the number of test items by 3 means there will be 3 times as much error variance. That means there will be 1/3 as much relative true score variance. So we start by dividing that initial reliability estimate by 3. Same thing as multiplying it times 1/3. All right, one way to represent the concept of dividing the reliability by 3 is to subtract 2/3 of the reliability from itself. We started out with 3/3, so if we want to get down to 1/3, we've got to take away 2 of those thirds. 3/3 minus 2/3 leaves us with 1/3. But just like before, doing this knocks our numerator off of the 0 to 1 scale, so we need the denominator to yank it back onto the appropriate scale. Once we simplify this denominator, you can see it's just like before. Before we were adding however much to the top and bottom. When we decrease the test length, we're subtracting the same amount from the top and the bottom. And I think if you've been following along throughout this entire process, this formula should be starting to seem pretty intuitive to you. Ideally, it would even start to seem kind of obvious, knowing what you now know. And I'd argue that's the level of understanding you should always be shooting for, at least with any formula that you're going to use a lot in your career. And the nice thing about understanding a mathematical concept at this level is that memorization becomes less necessary. Remember how we built that one version of the formula from scratch just based on our understanding of how the process worked, and then that formula turned out to be equivalent to the standard version? True understanding removes the need for memorization, at least to a large extent, and that's what you want to shoot for. Okay, if you've watched this far, you now have a fairly advanced understanding of the Spearman-Brown formula. I hope that how it works now seems much more intuitive, if not bordering on obvious to you. And I hope you'll apply this same sort of approach to trying to understand the other formulas that you learn about when studying psychometrics, statistics, and related concepts. In the next video, I'll discuss some useful applications of the Spearman-Brown formula, and I'll also show you how to set it up to automatically calculate in Excel and R. If you have questions or comments, shoot me an email. Otherwise, have fun.